Q series and Bloch groups.
So, thank you very much. It's a great pleasure to be here at this conference back in Japan. So, if I put this here, I can take off my jacket. Okay, now I'm connected to myself and not to my jacket. So I want to talk, there will be a little bit of overlap with Professor Olski's talk, but maybe not too much. I want to talk about several related pieces of work, all of which are together with Stavros Varoufalidis, who's sitting here. And the last part is also together with Frank, initial because there are two, Frank Caligari. So I'll mention Caligari again when he comes, but everything else you can imagine is with Stavros. So I want to talk about also the asymptotics of the Kashaev invariant, the volume conjecture, which is in the title of this conference, but especially from the point of view of number theory. So perhaps I remind you very briefly, anyway, we saw it today. So we have, if I have a knot and an integer, a positive integer n, we have the Kashaev invariant n, which is defined in some way that I won't repeat at all via state sum formula using the quantum dialog. But there's a different description which was found by the two Murakamis who are in the front row many years ago, which says that I can also get this using the colored Jones polynomials. Well, actually the same n. So there's a sequence, let me just put n here. There's a sequence of polynomials. The original one for n equals 2 was defined by Jones, and then these are the colored ones. Again, I'm not going to give the definition, but the theorem is that this thing is simply Jn for this knot of e to the 2 pi I over n. So that is, in some cases, an easier way to calculate it than from the state sum. Sometimes it isn't. And so, of course, the volume conjecture is the most famous statement. I keep looking at my notes because I don't want to forget things. If you take the log of the Kashaev invariant, it's supposed to grow exponentially, and this goes to the volume of the associated manifold, so let's say S3 minus the naught, I'll just put volume of S3, over 2 pi, and actually this should be the complexified volume. You should add I times the Chern-Simons invariant. So I want to talk about things that are a refinement of this. So let me start with an example. If K is the 4-1 knot, which everyone has seen, so the simplest hyperbolic knot, in this case the volume conjecture has been known for a long time. It is very easy. Otherwise, there were almost no cases of hyperbolic knots except 4-1 for which it was known. Ignat Kashaev proved a few, and today we heard about many more, up to 7 crossings. But in general, of course, we don't know the volume conjecture. Some of what I say will be conjectural, this part, and I want to go much further than the volume conjecture, and I don't care that we don't know it. But in this particular case, I can say what the polynomials are. I'll drop the k. It's the sum n from 0 to infinity to n minus 1, but I can also put infinity, you'll see why in a second, q to the minus nn times the product 1 minus q to the n minus j times 1 minus q to the n plus j. So if you look at this, you'll see that if m is bigger than or equal to n, then this term vanishes because one factor is 0. So it's really an infinite sum. Now, if you look at this just numerically, you find the following. Let me take q to be a root of unity of some large order. So the fixed idea is let me take the 300th root of unity. Then if I look at Jn of q for the 4-1 knot at this zeta 300, so the standard one. When I write this, I mean the standard 300th root of unity. Then I find that, first of all, this is less than 25 if n takes on the values 1 up to 299. But if n is 300, then it's 4.89 times 10 to the 45. So you have this very erratic behavior that the function is...
Sorry, n is 300.
Yes. Thank you very much. Yes, 300. So when you get a kind of a resonance and the thing is exponentially big, and of course it's this Jn of Qn, which is exactly the one that's meant to be exponentially big. And then you can ask what happens for 301? Well, it's periodic. This is period 300. And so if you think about it, there's a nice way to write it. What I'm saying is if I made a graph of this function, it would be very small, and then it would have this huge peak, 10 to the 50, and then repeat periodically. And I'm interested in this number, but since it repeats periodically, I can go backwards and go to 0. So I can just call this J0. So that's a very convenient way to do it. So let me rewrite the Murakami squared theorem as simply J0k of e to the 2 pi I over n. But in fact, this is not just true for e to the 2 pi I over n, it's true for any root of unity. So if zeta is a root of unity, then I can define J0, and I'll put the naught if I need it, of zeta as the value of Jn of zeta for any n such that q to the n is 1. And then those n's are, of course, all multiples of the smallest n, and it's a common value, and 0 is such a multiple. So that's the invariant. And in the case of the figure 8, which is what I said, so if k is, everything out here was general, but if k is 4, 1, then this is the following exact number. This formula was proved, the leading terms, by Anderson and Hansen, about 10 or 15 years ago. And then the more precise formula that I'm going to give was proved by Garoufalidis with various collaborators, or by myself independently, but it's quite elementary.
This is by Jorgen Anderson.
Sorry?
This is by Jorgen Anderson.
No, I said who it's by. I said it's by Anderson and Hansen. There are two papers.
Okay.
This crude formula. And now the precise formula which I'm about to write is by Garoufalidis and various collaborators. I have their names, but maybe it doesn't matter. There are several. And by myself, but it's an elementary calculation. I'm interested in further terms, as in the talk today by Wolski. And what you find is that there's an entire, so this is, so to speak, the easy part. That's the Anderson-Hansen result. But what you find is rational numbers, or rational numbers times, well, there's no point giving too many numbers, but it's my trademark to always give many numbers, so I have to do it. Pi cubed over n cubed, and so on. So we have an entire expansion. I found this by numerical method to 30 digits, and later found a theoretical method which was much worse, and so I could only get 10 digits by the 10 terms from the theoretical method, but 30 numerically. And Stafford had a different theoretical method, he could get as many as he wanted. So we have this expansion. Now, the striking thing is that you get algebraic numbers times pi. So let me give another example, which is exactly the one that occurred in Wolski's talks. The second example, I take the knot called 5,2. So again, one of the very simplest hyperbolic knots. And then in this case, so what I'm explaining now is the so-called arithmeticity conjecture. I'll formulate it in a second. So this was made about 10 years ago, I think, on the one hand by Garoufalidis and Ley, and on the other hand in the joint paper by Dimov, Degukov, Lennels, and myself, we stated the same conjecture. So the conjecture is that what you're about to see for 5,2, which is only numerical, is always true. So if I take this J0 invariant of zeta n for 5,2, which is just the Kashaev invariant, then it should be, well, the way that the physicists write it is actually a very bad way, as I'll show you in a second. It should be essentially like this. They always write in the logarithm because they're thinking of Feynman diagrams. It turns out it's a very poor idea. So S0 is conjecturally, as you know, as I already said, the volume plus I times the Chern-Simons invariant. I might have some signs wrong. S1 is meant to be, I think it's equal to the Ray-Singer torsion, but this is all conjectural. We don't even know the volume conjecture in general. But the conjecture, the arithmeticity conjecture, says that for any knot, S1 should be a rational multiple of the logarithm of a rational multiple and not any rational multiple, but it should be in the trace field of the knot. I won't recall the definition, but for this knot, for 4,1, the trace field is q of squared of minus 3. And that explains that the pi, which is really 2 pi I, is divided by I squared of 3. And for the 5,2 knot, it's q of alpha, where alpha cubed minus alpha minus 1 plus 1 is 0. So this is a cubic field. And so the conjecture is that the leading term is algebraic if you pull it in front, but all the further terms are in the trace field. These are the higher invariants that we heard about. And in this case, I won't give S0 because it's in accordance with the conjecture. It's the volume, it's some dialog of the expression. But in this case, what you find on the computer, there's a very good way to interpolate these numbers. You can find as many as you want. So S1 is this, S2 is not just some complex number or some algebraic number, but it's in the trace field, so it's a polynomial, of course quadratic then, in alpha. So I'll just give 2, but we gave about 10 in this was a calculation I had done. It's in our joint paper, the one I cited. And so on. So you get an entire asymptotic expansion, but even this is not proved. Even this is experimental, and in general it's completely not proved. Even the volume conjecture is in doubt. So it's a very daring conjecture, but because there's a very good numerical method, given a sequence of numbers, to actually find these things to extremely high precision, like 100 digits, then you can recognize if they're in your given field, and it always works beautifully. With Stavros, we've done endless experiments of this sort, and it certainly always works. But then, what I want to talk about is the next stage. So several years ago, when I first learned about this from various people, like Stavros, Werner Nahm, Zagier, then I asked, well, why only look at the special roots of unity e to the 2 by in? So the first thing I said is, what if your root of unity, instead of tending to 1, it tends to minus 1? So let me take minus the standard root of unity. And so I did that, again using the numerical method, and I found again an algebraic number, which to extremely high precision, now it's proved, is 3 to the 1/4 over 2 to the 3 halves, times n to the 3 halves, times the same volume that we had before, but now divided by 4. So it grows like the 4th root, roughly the other one. And then power series with some more coefficients. Well, I have more, but maybe I'll skip them exactly like that. It looks very, very similar. And so this is what is called in mathematics boring, because it's exactly what you'd expect. It's exactly the same type of formulas here. The numbers are a bit different. This is a bit different. The power is the same. The Cn is slightly different. It's not surprising at all, and I wouldn't have mentioned it, except that it's false. What I actually found on the computer is that this was correct, except that sometimes you had to multiply it by 27. And sometimes it was correct, and sometimes you had to multiply it by 5. So this is back for the 4-1. I did the corresponding experiments for 5-2 at that time, and for many, many other notes with Stavros. But these particular numbers are back to 4-1.
Do you care about n is odd or even?
No. Just a second, let me continue the lecture, and you'll see. In 1 second, when I finish the sentence, this is if n is odd. So it's a good question. The answer is yes, I care, but I was in the middle of writing the equation. So what I found on the computer was that to extremely high precision, I got the identical power series in 1 over n, and the same exponential term, whatever n was, but sometimes it was multiplied by 27, sometimes by 1, sometimes by 5. So first this was a mystery, but then you can also look at the value of J0 of zeta. Well, I'll just put any nth root of unity. So in this case, well, if n is 1, it's 1. If n is 2, there's only one root of unity, the value is 5. If n is 3, the value is 13. If n is 4, the value is 27. If n is 5, there are 4 roots of unity. Here there were 2 roots of unity, of order 3 or 4, but they're complex conjugate, and this knot is amphichiral. It's its own mirror, so it's real, so it didn't matter. But here, depending which one you get, the one that we saw before that was exponentially big is this. And the other one, if you take, this is for zeta 5, and that's for zeta 5 squared. So you get 2 values, and then when you go to 6, it's 89, etc. this is the actual volume of this J0 invariant at these roots of unity. So now if you compare this, then you're, of course, immediately struck by the fact that these three numbers are the same, and that's not an accident. This is exactly J0 of 1 over n, well, 1 over n, sorry, J0 of zeta n, where 1 over n is equivalent to a half plus 1 over n under SL2Z. So depending whether n is even or odd, and if it's even, whether it's divisible by 4 or not, if you try to reduce this by an element of SL2Z, of course a half is equivalent to 0, but when you move n, it is not always equivalent to 1, it's either equivalent to 1, a half, or a quarter. And that's exactly this number. So what we're seeing here is modularity, and this led to the statement of the modularity conjecture, which is the thing I want to talk about next. So this sort of goes with the arithmetistic conjecture. We have also the modularity conjecture, which can be stated in two ways. And one of them, the easiest way to make it clear, is to show a picture, which, if it works, this will work. Now down. Is it now on, you think? Yes. I also have the wrong page. Now I need a password, probably. And now, of course, I didn't prepare and I don't know how to use a Mac, and I need a password. No, I can't do it because it keeps asking for a password.
No.
Okay. And now I have to... there, wait. Okay, I hope I can find this stupid picture. I didn't want to use a computer, and I certainly should have not done it. But I'm hoping to show you the pretty picture. Here we go. So that's a picture of the Jones invariant, which this dark j of x, I'll define in a second, it's j of e to the 2 pi ix. Because since this thing is exponentially big, if you graph it, it just is 10 to the 50. So this is a graph of the log as a function of rational numbers, and as you see, it looks very random. But now, I'll write this in a second. So let me write it and then show you the picture. If I define j of alpha, of x, where x is a rational number, to be this j0 for the given knot of e to the 2 pi ix, since x is a rational number, j0 of e to the 2 pi x makes sense. Now, when I'm graphing this thing, the first graph showed the log of j of x, but the second shows the difference of the logs of j of x and j of minus 1 over x. And you see it's a completely different picture. Instead of being kind of dense in the plane, it's turned into a curve, which is almost a smooth curve. It's smooth, it's a little unusual, it's smooth at every irrational point, C infinity, and continuous but not differential at every irrational point. That sounds impossible, but it's because when I say that it's smooth at every rational point, like here, C infinity, it's C infinity from the left and C infinity from the right, but it jumps. Whereas at the irrational points, it does not have a derivative at all, but it's continuous. So it's continuous but not smooth most of the time, and smooth but not continuous at the other points. It's a little strange. Okay, so this is a picture of the modularity. That's all I want to show you. So if I can successfully turn this all off, then I can continue with the lecture. So that's one way to state this modularity, that the difference between log j and log j of minus 1 over x is a good function. But there's a different way that I found after some fiddling. If I take this new variable x, which is now in q, or actually it's in q mod z, but I prefer to work in q. Okay? So if I take this rational number and I apply any element now, not just minus 1 over x, any element of the modular group, then what I find experimentally, and this is the conjecture, the modularity conjecture, cx plus d to the 3 halves times the original function j of x times this volume, the same volume times x plus d over c, times a power series in 2 pi I over cx plus d. But it's not one power series. You already saw in my examples that we had one power series at 0, at 1. That was this one. 1, 11, 6, 97. But at minus 1 for z, which is 1/2 for x, we have a different power series, 1, 41, 36. So for each alpha is just minus d over c, which is the point that is sent the inverse image of infinity under this map in SL2Z. So there's a square root term, an exponentially big term, there's a power series like we saw, and then there's this mysterious extra factor 27, 1, or 5, and that's the j of the original thing. So think of x as being a small fixed rational number. That would give the 1, 5, and 27, and here, well, sorry, in this version I want x to go to infinity, and then this is the relation. So this has many consequences. For instance, a partial answer to a question that was mentioned in Olski's lecture. But the modularity, you don't only have to look at -1. You can even look at the J0 invariant of e to the 2 pi I over n. But let's say that n is not an integer, but it's an integer plus 2/5. After all, that's also a rational number. So I can still do this. And you notice that this would be the same as e to the 10 pi I over 5m plus 2. So this was the question asked at one point in his lecture about e to the 6 pi I or e to some multiple of pi I over an integer, but then it will depend on the congruence of this integer mod 3, or in this case modulo 5. So now if I do this, even in this case, then I'll get the same series that we had before. 3 to the -1/4 times n to the 3/2 times e to the cn times 1 plus whatever it was, 11 over something n. It'll be exactly the same formula as before, except that there'll be a factor here, and this factor will be 46 minus 2 squared of 5. So you will, if you look at this particular thing when n goes to infinity through numbers of the form an integer plus 2/5, then you'll get exactly the same asymptotics to all powers in n, not in n, except that there'll be a numerical factor which is exactly the value of J0 of 2/5. So that's the modularity, that because it should really be -1 over m plus 2/5, but since my particular function is even, it doesn't matter. And then you see -1 over x is in the modular group. So if I apply -1 over x, I get m plus 2/5, and then my function is, sorry, this is j. My function is periodic, and so I can forget the m, and so I just get 2/5. So that's...
So it's opposed for all nodes or...
Well, the conjecture. There are two words here. There are two words here, modularity and conjecture. This is for all knots. So I conjectured for all, and by now we've done about 10 knots in great detail at many roots of unity to very high order with stoppers. It always works for many knots, but it's now completely proved. Originally, I conjectured from my paper on quantum modular forms. I only gave the complete details for 4.1, but that was conjectural. Now it's completely proved. It's also in our paper. So one case is proved. As I said, you cannot possibly prove the general case because even the volume conjecture is a conjecture still. So this is very much more detailed. Let's talk about higher order terms to all orders. So somehow I keep feeling I'm walking off the end of the step. Oh, there is no step. Okay, so now I want to tell a somewhat different story. So I hope I kept this power. Now I erased the important power series, but maybe it's still there. So this was an accidental discovery, again, of, I'll just put SG for Stavros Garifalidis. It's too long to write Garifalidis. He was studying something called quantum spin networks, and that led him to, so I'll use the standard notation, the Q, Bloch similar Q factorial, so 1 minus Q up to 1 minus Q to the n. He was led to study the following series. Well, this factor isn't there, but I'll include it. It's Q to the power 3n squared plus n over 2 over Qn cubed. And so he said, let's look at the asymptotics, because he was interested in the asymptotics of this for his own purposes. And so this is an explicit power series. You can compute as many terms as you want in the Q expansion. But the question is, what happens when Q tends to 1, or maybe to -1, or a cube root of unity, and so on. So as you go to the unit circle, let's say radially, along lines. And what we found after a lot of work was we found expansion that worked. So you write Q as always is e to the 2 pi tau, like number theorists do work with modular forms. Tau is in the upper half plane. So now tau is tending, in this case, to 0. So Q is tending to 1. And then what we found is that to all orders, and it didn't even matter how tau tended to 0, it didn't have to be radial, it could be in any direction, to all orders, we found this expansion where phi hat is exactly the same function that we had before. It's e to the c, which was the same volume for the 4-1 knot. This is times the power series that we had before, 1 over the 4th root of 3 times 1 plus 11 pi over 36 square root of 3 times x, and so on. I may have some 2 pi i's wrong, but it's essentially right. In other words, the very, very same power series that you find, which in this case is proved for the asymptotics of the Kashaev invariant, turns out to also give the asymptotics. This is a Q series, as in my title. It's a function that, unlike the Kashaev invariants or my J0, or the original J0 is defined for Q, which is the root of unity. So it's only defined at a countable set of points. And similarly, J of x, which was set Q as e to the 2 pi x, is only defined on Q, which is a dense set in R. But a Q series is defined not at the roots of unity, but in the interior. And so here we have a strange relation between the radial asymptotics when you go to a point of the function defined in the disk, and the others you have a function defined only at rational points. But if you fix a rational point like 2/5, and you approach it through rational points and look at the asymptotics, you get the same kind of series. And we played with this some more. The same is true at all roots of unity. If you take G going to other roots of unity, you get a corresponding story. So there's a further series from this that I was going to tell, but I'm going to skip. I'll just say that in his work with Kashaev, Stavros was led to find, with Rinat, I guess I'm using first names, was led to find another power series which was related to, well, there are many things. There's the index of Guyot, Gukov, and Dymovde, and there's the Kashaev-Luo-Vartonov invariant, and for both of them, they needed a certain power series, which, well, I could just write it down. M goes from 0 to infinity, minus 1 to the n. It's again a non-type sum, so I'll define it in a minute. So it looks like this. That's very similar, but then there's an extra term, E1 of Q, which is kind of a fake Eisenstein series, plus a finite correction. And this thing is 1 minus 4 times the sum. 1 plus 4 minus 2 to the n. It doesn't matter. It's an explicit power series. And they found that the G also, or we found maybe, now I don't know who did what, that this had similar asymptotics. And they also found that this wonderful index of Dymovde, Guyot, and Gukov for the 4-1 knot, conjecturally, factors as the product of these two completely different series which come from completely different thoughts to do with quantum invariance. So I'm only saying this very briefly so that those people who have heard of some of these invariants and are interested can ask, preferably Stavros and not me, questions and find out more of the story. So that is one direction, one connection with Q series, that you have this remarkable thing. So I wrote this 5x because this is my original 5, which is a power series. So this is a power series, in this case, with real coefficients. Okay, and then as a consequence of this, we also found something very cute that I did want to mention, if I can find my numerical notes. If you take this same C, remember C is this stupid constant, which you can compute in terms of dialogue limits. It's the volume of the complement of the 4-1 knot divided by 2-5, so it's 0.323 something. So it's some very transcendental number. Phi, on the other hand, has all algebraic coefficients. Maybe I won't include the pi, I don't remember anymore. And now, but this phi is a typical asymptotic series that you get in such things with Feynman diagrams. It's factorially divergent. The nth coefficient, I don't know, it's proved, but experimentally, the nth coefficient grows like n factorial. Here, in fact, it's probably proved. So this is not a power series that converges, it's a formal power series. But now, because of all of these relations, if you believe all of the asymptotics that we found here and this identity, then you find that the following statement has to be true, and we checked it, and it is true numerically to very high precision. You take this strange combination of that original power series with algebraic coefficients, and you take this strange thing, phi of 2x over 1 plus x times 5 minus 2x over 1 minus x, but then multiplied by e to this strange number, and then you subtract a similar thing here, but with e to the minus c. And then this thing is some new power series. Obviously, it's a formal power series now, completely not algebraic at all anymore, it involves the C. But now this converges for x big less than 1. So what was factorially divergent suddenly turns into a power series. And let me illustrate that just numerically by giving you two coefficients. So if n is, let's say, 20 or 100, I can ask for the coefficient of x to the n in the original power series 5x, and then I can ask for the coefficient of x to the n in this new power series q of x. And so here's the table. This is 3 times 10 to the 20, and we have lots of digits, but they don't matter. This is 3 times 10 to the 74. But this is minus 0.01, and this is minus 0.01. So here the coefficients are absolutely huge, but here they're even going slowly to 0. So the thing converges in the unit disk. So that's kind of a beautiful thing. So now, in the remaining time, which is about half of my time, which is good, because it's the part I'm most interested in. Now I can slow down, I hope. I want to tell about the most interesting part of this, which started with the numerical observation that I made when I did all of these calculations for the 4-1 knot. And there were some algebraic numbers. But if you're not a number theorist, all algebraic numbers are the same. It's just some algebraic number. It's in Q bar. But if you are a number theorist, then of course they're all a little different. And these were really kind of amazing. And so I wondered whether there's any meaning to these amazing numbers. And luckily I asked the right person, it was Frank Caligari, that A was interested and B had all of the thoughts and was able to solve in one direction, and then together we did another direction. So let me give you a little more of the numerics. So I should go back to my original table. Where was the important number? I know I wrote it down because I remember copying the numbers today, but I can't find on which of the many pages it's written. Actually, there aren't so many pages, there are only 5, and they're carefully numbered from 1 to 5. It shouldn't really be very hard. 2, here it is, it's in big letters, it's on page 2. Okay, so let me give the example. So in this expansion, maybe you remember, but it's still written. It's usually called h bar, but I'll call it epsilon. So epsilon is very small, infinitesimal, and alpha is a rational number. And so remember, this is the story that I told you, that as you approach, here epsilon would be 0, here epsilon would be a half, here, sorry, not epsilon, alpha. Right? It corresponds to e to the 2 pi alpha. As you approach this, we got a certain power series, which is 1 over the 4th root of 3 times 1 plus 11 over something times x, and so on. But here we got a different power series with some other constant, and a 41, and so on. So we get a collection of lots and lots of power series. Now, the complete conjecture, I never said. You can combine the arithmeticity and the modularity conjecture. See, the arithmeticity conjecture is only about the original case, j of 1 over n, corresponding to e to the 2 pi I over n. But of course, this is the same under the modular group as j of 0, which is just 1. So now it's just phi 0. Well, there's a power of n, and the exponential term, essentially, it's just the power series 2 pi I over n. So the usual expansion that you see for the volume conjecture and its refinements, as in the lecture today about the asymptotics of Kashaif, is only the case alpha equals 0. And then the conjecture, remember, was that phi 0 of x, or phi 0 of epsilon, I'm now writing it, is a power series whose coefficients are algebraic up to a constant. And the constant is a little more complicated. The constant front, like in my example, it was the 4th root of 3, which is not in the trace field, which is q squared minus 3. But once you took out that constant, then everything was supposed to be in the trace field. Now in the algebra, you can combine them and say in the modularity conjecture, we have not just one power series, phi 0, but infinitely many, phi alpha, and then phi alpha should be a constant, depending on alpha, times, and then what's left will be a power series with coefficients in conjecturally in Fn, where Fn, well, F alpha I can call it, you just adjoin e to the 2 pi I alpha to your original number field. So it's a cyclotomic extension, but if alpha has denominator n, it only depends on the denominator, so I call it also Fn, drawing the nth root of unity. So we have this conjecture. And that worked beautifully in all of these examples. I mean, I gave you some of the numbers for the case of 52. So remember the way we originally wrote it, because that's what the physicists liked, was with this e to the s0 plus s1 and so on. When you did that, then the s2, in the case, this was for the 4-1 knot, and the alpha was 2/5. So now you have to be patient for a second and look at some specific numbers, because this will make very clear that something non-trivial is happening. So what you got is 2,678 minus 943 epsilon 1 plus some more numbers where zeta here is the standard cubeword of unity inverse times e to the power 2 pi I times 2a over 5. So a here could be 1, 2, 3, or 4. So I take it back. I'm not just looking at 2 over 5 and a over 5. I'm doing them all simultaneously. And then epsilon k is zeta to the k plus zeta to the minus k, and pi 29 is 2 minus epsilon 1 plus epsilon 2 plus 2 epsilon 3. So here there are two more terms with epsilon 2 and epsilon 3. And you have this number pi 29, which is a divisor of 29, and it turns up in the denominator. So in this kind of a game, you expect the numerators to be very complicated, but denominators should have only small, obvious primes. But here there was this crazy prime. And then when I went on my computer and did S3, there was something else in the same field. So this is in the field of here of 15th roots of unity, because I started with the cube roots of unity in this particular number, this particular knot, the trace field, the cube roots of unity, I've added a 5th root of unity. But now I got pi 29 squared, etc. And each time I got bigger powers. So I thought this was some very deep thing, but it turned out I was doing the wrong thing, and the right thing, none of the physicists were doing it today, but I was very happy that in Olski's lecture today, he did the right thing immediately. You should not write this power series as e to the something times x plus something times x squared, and which the physicists always do because the thing of finite diagrams. You should write it as 1 plus kappa 1x plus kappa 2x squared, etc. You should write it additively, and actually not kappa, because you don't necessarily have to take out 1. There's a natural constant term, whatever it is. So you want to write the whole series as some constant times the power series, and when you do it here, additively, you find that you get a strange number times kappa 0, which happens to be pi 29, plus some other simple number times epsilon plus something times epsilon squared. So the power series is a perfectly good power series with coefficient f. There are no special denominators or very small denominators. But when you take the log, then you have to first divide by pi to the 29 and then take the log, and then you get all these powers. So that's a complete red herring. There are no strange numbers in the denominator. It's all small denominators. But what you do find is that whatever you take out, you don't have to take out the full constant term. So you can put it's not a good idea, because if you took out the full constant term and started with 1, then you would have pi 29 every denominator. You should take something, but there's some peculiar number in front. Even no matter how you normalize it, this thing is not in the trace field, or rather this power series phi alpha is not, even experimentally, in this field f alpha, which remember is adjoining the root of unity, the trace field. Well, now it's a power series, so I can just call it x. It's not in that, but it is in that times a constant. But what happens is, in the case that I was doing alpha is a over 5, I think I can write down what the constant was. The constant here was, first of all, there's a square root. You always get some square roots. That's from the saddle point method and Gauss's method. And here what you got was something very weird. You got the 10th root of the product epsilon 2 over epsilon 1 cubed epsilon 3, where these are the same epsilon k's that I defined. So these are units. So this is the 10th root of an algebraic unit in my field. But that is something very, very strange in number theory. Why are we getting not a number in our field, but the 10th root of a number in the field? So that part I'll just say now again, I'll repeat very briefly. For every knot, and we've looked at many cases, different knots and different expansions and different roots of unity, we always find such an expansion. you can factor out something, and what's left is in this field F alpha, and there's something that's a rather dull thing involving only the bad primes here, 5 and 3, the square, that's always the square root, but then you'll always get an mth root or 2nth root here, the 10th root of a unit. And so the question was, if that's true, can one predict that unit? Can one say what is the number that you have to remove? So I asked Caligari, and my guess was it had to depend on this. If you have your 3 manifold, it is a class which lies, at least up to torsion, in the algebraic K group, K3 of Q bar, which is the same as the Bloch group. And conjecture also the same as the Bloch group of C. The Bloch group, I'll just remind you very quickly, it's formal combinations. The Bloch group of any field is formal combinations in Z or in Q of numbers in the field with the property that the sum x wedge 1 minus xi vanishes in the exterior square of f cross, and then you divide by the phi formulation. So if you've never seen this, one needs several minutes to understand this definition, then just forget it, but most of you have seen it. The Bloch group is something that you can really work with and compute with. And the Bloch group is known by theorems of various people, Suslin and others, to be essentially the same as K3. And there's a canonical, essentially from the Hurewicz theorem, a 3-manifold has a canonical class there. But in the case of the Bloch group, you can really see it. You triangulate your M as the union of some delta i's, and you can do it with ideal tetrahedron. And then just as in, again, Professor Otsky's lecture, if I take the 4 verses of the ideal tetrahedron and take their cross ratio, then I get a number, and those are exactly the sum of those numbers is the element of the Bloch group. So at the level of the Bloch group, you just take a triangulation, and you get this, and if you change the triangulation by a Pachner move, that's exactly a 5-term relation, so you get a well-defined element. But there's also an abstract element in K3, and they correspond. So we have a class in K3, and so to summarize what I've said so far, if I have, well, think of the manifold, but you could, in my case, it's S3 minus a naught. I'm sure there are versions of this for closed 3 manifolds. If I have this and a number, n greater than or equal to really a number, a rational number with that denominator, depends slightly on the numerator also, then on the one hand, I get a specific root. Let me forget the square root, so I'll square it. But I get nth root of unity where I get some unit, algebraic unit, in the field where I've adjoined an nth root of unit, and I get that for all n. Well, it's not quite only Fn, as I say, it's F alpha. If you conjugate alpha, it's the same field, but you have to conjugate epsilon. So the field only depends on n. The alpha actually depends on itself. So I get this, but I also get a class, psi m, which is in the Bloch group. And in fact, here it's in the Bloch group of the trace field. And so the question is there perhaps a purely algebraically defined map which goes from algebraic K theory of any number field? Now forget all topology. Can you simply define a homomorphism from B theory of F for any number field into the units? Now, usually in number theory, there's no way to compute the units of anything, so it's impossible to imagine a map that creates units. But it had to exist because of this experiment, or these experimental facts. So now, if you think slightly more, this number was not quite defined. Because remember, to get this number, I had to factor, I still have a pi 29 here. This number was not the exact constant term. As in the lecture this afternoon, where it was a constant omega times 1 plus. For the algebraic number theory, that's a bad idea. I don't want to divide everything by pi 29. So this power series may have a non-trivial constant term. I want to take out something interesting that is not in the ground field. But of course, if I change this root of unity here by the 10th power of a root of a unit in my ground field, then its 10th root is in the ground field, I can put it here. So I can put it back and forth. So there's no way to know what this is except up to 10th power. And therefore, I'm actually only getting, I want to get a canonical map, but it only should go into the units modulo nth power. So now it's at least imaginable that you can do that. And then that is the advantage then if you do that, then since this thing is a torsion group killed by n, then of course, I'll just put over n times B3 of f, of course it'll factor. Now the next thing is, when you do this, there's a Galois action here, and from the experimental data, I found that this was in the chi inverse component. That I'd already seen experimentally, where chi is the standard, the so-called Teichmuller character. I just remind you briefly, chi is the map from the Galois group of Fn over F. I'm assuming that the nth root of unity is not in F. So I take the Galois group and identify it, in that case with Z modulo Nz star. And the identification is simply when you take any element in the Galois group and apply it to your nth root of unity, it's again an nth root of unity, so it's some power, and that power is called chi of sigma. So that's the famous Teichmuller character, and here you take eigenfunctions, eigenvectors with that eigenvalue, with the eigencharacter chi inverse. And so what we finally proved is actually two theorems. This is all in the work now with Caligari, but the second one is completely his work, and the first one is also mostly his work. Sorry, this is just the Bloch work, excuse me, there's no 3 here. But this is K3. There exists canonical maps that do this. I'm assuming here various things, that zeta n is not in the field, n is prime to some number, f defining it like, in our case, n should not be reduced by 2, 3, or 5, in the 4-1 case, and n is square free. So let's say big primes. That's not the main point. There's a canonical map, and what's more, they're both isomorphisms. Of course, these groups are already known to be isomorphic, but we don't know the comparison between the two maps. So they're completely different proofs. This is essentially all Caligari. It uses the algebraic K-theory definition of C1. So there's some theory of Chern classes in algebraic K-theory, and some fairly sophisticated algebraic number theory. This one is completely explicit. And so if I'm still okay for time, let me write down what that map is. So then that makes the theorem much more precise. I'm claiming take the following map, then it lands in this group, and what's more, it gives an isomorphism. So the definition of the map is somehow very, very pretty. So let me define the map. So I have my classic psi. Remember that the classic psi was a combination, a formal combination of elements in your ground field with coefficients, let's say, in Z, a finite sum. And you should think of those finite sums as you take a triangulation. If it came from a 3-manifold, you take an ideal triangulation. Each one is a cross ratio, and then you take them plus or minus depending on orientation, and this is the cross ratio of the vertices. That's the correct element of the Bloch group. So this is supposed to be an element of the Bloch group, and because these numbers are in a given number field F, it's in the Bloch group of that F. Okay? And now I make the following thing. I first define, so I've also fixed a root of unity, which is this e to the 2 pi I, well, it's just an nth root of unity, primitive. Remember in the story that I had before, you had to tend to not just 1/5, but also 2/5, 3/5, 4/5. So zeta would be e to the 2 pi I times 1/5, 2/5, and then it conjugates in the right way under Galois. That's a detail, but when you do this map actually depends on a particular zeta. So I shouldn't have just picked zeta, I should pick zeta, which is an nth root of unity, primitive. And then I'm taking the f zeta is just f u join zeta. So that's the cyclotomic field. The field only depends on n, but this map, we call it D, I think, forgotten R. This map, both maps, depend on R. So the other one we called C. So both of them depend on zeta. So this is C zeta because C is for first Chern class. So here's the definition. I define, we call it, I don't know if it's a good name, the cyclic quantum dilogarithm. So we're fixing the root of unity, zeta, which is, remember, an nth root of unity. So similar functions have been written down by various people, including Kontsevich, in somewhat different context. So you take this completely explicit function, so this is just a polynomial with coefficients in q of zeta of t, it's just a simple polynomial. And now, if I have this element of the Bloch group, I define P, depending on this root of unity, of Xi, as the following thing. It's the product over all I. You take d zeta of Xi, but you have to normalize by d zeta of 1. Okay? And then you take that to the power ni. In other words, you just add it up over the elements of the Bloch group. So, and here the Xi, sorry, of capital Xi, where capital Xi is some nth root of little xi. So you take these original things, which you can think of as the shape parameters of an ideal triangulation. So for instance, for 5, 2, there's specific numbers in Q of alpha. Alpha was that third degree irrationality. But now for each xi, you pick some random nth root. But it's the same, in this form, it's the same one. Then you check with a lot of work that this thing belongs, this whole thing belongs to my Fn, which is the nth root of unity, it's a multiplicative group, times some h. So this thing is a Kummer extension, h for Kummer, I don't know why. You adjoin all of these nth roots. We've already adjoined the nth root of 1 to our field. Now I join the nth roots of all of these other numbers in the field. So that's what's called a Kummer extension. You have a field where you join the nth root of 1 and the nth root of a lot of other things. So this is some specific Kummer extension. So by definition, this thing, every term in this is an H cross. But the amazing thing is you can prove, that's a theorem, that this product up to nth powers in that Kummer field is in a much smaller field, maybe the original field, Fn cross. So then you take this factor. Of course, this factor isn't unique. If you multiply it by an nth power, you could put that in here. So this is only, call this lambda mu to the nth. Then the element lambda is only defined up to nth powers. And so that's the map, and then you prove that that is a well-defined map, that it lands in the correct Galois isotypical component for chi inverse, and what's more, if n is square free and prime to all these things, it's a unit, and what's more, it's an isomorphism. And as I say, with a completely different argument, coming from algebraic K-theory, you construct in a completely different way. There's no Bloch root, now there are no xi i's. You use algebraic K-theory and algebraic number theory, you compute a different map. But we know that these things are canonically equal. And so you can try to compare these two maps, and based on a certain amount of evidence, actually quite a lot of evidence, we have the conjecture. So the theorem is, first of all, that R zeta, that one of these maps is a power of the other. Of course, the power is only defined modulo n, because everything is only defined modulo n in the exponent. But the conjecture is that, in fact, gamma is universally 2. So these are essentially the same map, up to slight rescaling. And we've half proved this, so I'll just say a word about that. It's kind of amusing. Let zeta be a p-th root of unity, primitive p-th root of unity. And now I take psi to be the sum, 0 less than k less than n, then p, in this case, of zeta to the k minus zeta to the minus k, over zeta minus zeta inverse. This is in the Bloch group of, in this case, Qn, of the corresponding field, Q of zeta. You check that. Oh, it's more, it's torsion. So this element in the Bloch group is killed by n. It's a kind of a known expression. So this is a specific thing. And now, if you believe certain abstract conjectures, just commutativity of certain diagrams that Caligari says he should be true, but he doesn't know how to prove them, then when you compute the Chern class map of this, it seems you should get some nth root of unity in this case, because it's torsion, and the root of unity you seem to get seems to be zeta. So he believes that that's true. This is only conjectural. But R zeta of psi zeta, we managed actually, Selfers managed to prove it's always zeta squared. This is actually true. And so at least half of the thing we've done to get the two, one of them is we expect to be zeta, and it always is in every experiment. The other should be zeta squared. And the proof of this is also very amusing. The second thing, you can also look at num sums, which I'm not going to talk about, but I've had several sums today, like 3n squared plus n over 2 over qn cubed. A num sum is a similar thing of that sort, with the Pochhammer symbols below, maybe multidimensional. And we actually proved a theorem for any multidimensional number sum that the asymptotics in all roots of unity are given by a very specific formula, and that formula has exactly the same nature as in this conjecture. It's the product of a power series in epsilon with coefficients in the ground field adjoining the nth root of unity, times a constant, and that constant is the nth root of a unity, and there it is really this, well, there we can prove it. Here it's just a guess. So for the nom-sums, we can prove that the asymptotics of the nom-sum, a typical nom-sum would be q to the n squared over qn, the one you see in Broda's Ramanujan. If you look at the asymptotics in all roots of unity, then we can prove that at every root of unity, you get a whole power series with coefficients in that ground field up to an nth root of a unit, and that nth root is exactly the one given by this theorem. So now what Stavros did, he took a particular nom-sum called the Andrews-Gordon identity, depending on the prime p. When p is 5, it's exactly Broda's Ramanujan, but it's a famous generalization by Andrews and Gordon. That nom-sum, by our theorem, we know the asymptotics, and it involves this number r zeta. But in that case, the nom-sum is modular, because that's the theorem with Andrews and Gordon. It's a specific product of eta functions, so we know it's modular. So we can compute its asymptotics a priori. And when you compare the known asymptotics from the modularity with the asymptotics coming from our theorem that the asymptotics in any nom-sum involve this funny construction, then you compare, then you find this. So at least we've done half of this comparison. So the proof jumps back and forth between analysis, topology, and algebraic number theory in a rather subtle way. I meant to tell you two other things, and I meant to talk much more slowly, and the two would have been a good combination, but I failed on both points. So I think I'll just stop early rather than try to make you even more tired. So, thank you.
Any questions?
I'd like to know the statement, more precisely the statement of this theorem. Do you use some three-dimensional geometry for this, or
there's no geometry in this at all. In neither one, there's no geometry. It's all algebraic number theory, completely algebraic. So this uses the its work of maybe Soulet and people like that on abstract Turing class in algebraic K theory. One thing that I should say, that work, here you see an index K3. There's also K5, K7. I mean, according to Borel's famous theorem, the even K groups for number fields are, if you tensor with Q at least, are trivial. K3 is the one we care about for 3 manifolds. It's the same 3. If you had a hyperbolic 5 manifold, it would have a class also in K5. So one can add, of course, you don't have all the rigidity, Thurston theory, this whole story doesn't exist, but you can still ask, what if I take K5, K modulo n? And now there is also a Bloch group. So in general, if you put K2m plus 1, there's also a Bloch group, which I defined many years ago, but it's conjectural, except for n equals 2, where my conjecture was more or less proved by Blanchard. So in general, we don't know that the two groups are the same, but they behave in a very similar way. The higher Bloch groups are defined the same way as here, as combinations of elements in the field satisfying a relation, modulo some relation. So you can work with it, and the K theory is defined. And in principle, we haven't completed it. We can do both of these theorems independently. And that actually gives the strongest evidence till today that my conjecture was not crazy, because we get, for these higher Bloch groups, it maps, it's exactly the same, except this is not chi inverse, but chi to the minus 2, chi to the minus 3, and so on. That's all. And this is B2, B3, B4, and this is K3, K5, K7. And we can prove it on both sides. So it's not known that these things before you divide by n are the same. But this shows that after you divide by n, they are the same. So in principle we can do, so it's completely algebraic, and if it were geometric, we couldn't do anything in higher dimension because there's no geometry, no geometry that anyone knows. So this is an algebraic story. And maybe one last thing I should say, the reason Nam invented these sums, maybe many of you have seen them. In the one-dimensional case, it is the form of quadratic formula. It's always written half en plus c over qn. That would be a one-dimensional Nam sum. With a two-dimensional Nam sum, you'd have two n1 and n2 and two Pochhammer symbols, and so on. And he observed that sometimes these things are modular forms or modular functions, but very rarely. For instance, for the one-dimensional, he conjectured, and I proved, that there are exactly 7 triples of rational numbers, only 7, where this thing is modular. So it's extremely rare. And now, many years ago, asked, when could this be modular? And he made a conjecture that's not completely precise, because it doesn't say exactly which triples A, B, and C, but it tells you which A. And the A have to each A, which here is a number, but in general a matrix, he associates an element in the Bloch group. And that element must be torsion. That's part of his conjecture. So we now believe that we will be able to prove one direction of his conjecture, namely that if you have a Milan sum which is modular, that you get torsion in the Bloch group. We think we can prove it using this because since, as I said, we have a theorem given the asymptotics of the Bloch group in terms of this. So if it's modular, just as in the special case that Stavros worked out where you got the same square, it worked because this was torsion. And it's always torsion when it's modular. That's part of his conjecture. So if it's torsion, then you compare the two things that we know. The fact that it's modular gives you asymptotic information. This theorem gives you other asymptotic information. And when you compare them, you find it will, we hope, that this has to be true for all large primes. You will get 0 in this group for all large primes n. Because n, if it were square free and prime to something, so all large primes are good, you'll get 0. But if a number is divisible by n for every large prime in a finely generated group, it's 0, or torsion. So we think we will, if we haven't yet completed it, but another corollary of this thing, which is pure number theory, it has nothing anymore to do with topology, but it was all motivated by the asymptotics of the Kashaev invariant. So it's a mixture of starting with volume, with geometry, and then abandon.
Any other questions? Okay, let's thank the speaker again.